Working. Okay, thank you very much. Okay, so let me just get ready here. So what I will talk about are Zeta and L functions, and in fact, since I suppose this is an hour talk, I thought I would include some sort of account of where some aspects of the subject lie. Oh. Well, I'm sure it's better when it's working. Thank you. So I want to discuss the Zeta and L functions and discuss some aspects of where the subject lies today. In the 50s, 60s, and 70s, there was a lot of marvelous work on the theory of Dirichlet L functions and the Riemann Zeta function. In the last 10 to 15 years, I think you could say that the subject of L functions for modular forms and quite general L functions is moving to the position where it's at the same level of understanding. Of course, the big problems still remain unsolved. I'll get to those. But one should always remember that in the subject, while one doesn't have to always conquer the big problem to solve some problems completely and unconditionally, one doesn't have to go over the mountain. There are many instances where we go around the mountain. And so the subject has been nevertheless very successful, even though the real major problems are still mysterious and will be the main focus of the talk. I noticed that talks have really gotten better over the years. When I was younger, in regular math talk, you'd often have the lecturer lecturing on his face or something like this, because every time you look behind to see what it looks like, it looks good, but then you move back in front. And I never know whether you're supposed to look there or there. I will look there, and if I'm blocking the way, please shout. So I will start at the beginning. And in fact, it is the Riemann Zeta function that is the center of the subject. Though my theme, and this will be the theme throughout this talk, is families of L functions. For all the progress, I would say, in recent years is based on families, and this is the main emphasis. Okay, so let me introduce the beasts, the L functions and the Zeta function, and we will get more and more general as we go along. Not simply for the sake of generalization, but because in many instances the more general case is crucial in understanding GL1 objects, which I now introduce. So firstly, there's the Riemann Zeta function, which I hope most of you are familiar with. It's given as a series 1 over n to the minus s, which can be written as a product of 1 minus p to the minus s to the minus 1, which of course is easily established by expanding that inverse binomial and collecting terms, and all that certainly makes sense for real part of s bigger than 1, and unique factorization of primes establishes that identity. It is this connection between primes and the series, and hence this function of s, that makes the function so interesting. And perhaps still the deepest thing we know about this function, I'm sad to say, is the functional equation, which is what was pointed out by Riemann in a paper where he outlined the method to attack the proof of prime number theorem. So what he showed was that if you append gamma and pi to the minus s over 2, so we complete the function as it's called, this function, which I think he called Xi, Denninger certainly also introduced this function, satisfies a functional equation. This is completely equivalent to the Poisson summation formula, and it's a remarkable symmetry of this function, and it's certainly the central thing that is used over and over again in studying this function. As I said, we must look more generally. In fact, the following functions we introduced before Riemann. They're due to Dirichlet. He introduced them to prove his lovely theorem about primes and progressions. So what he introduces, if you take a character of the residue classes, invertible residue classes modulo q, and you introduce a multiplicative function which you extend to the integers to be 0 if m is not relatively prime to q, I will not be always completely accurate. There's a notion of a primitive character, but I assume that you'll excuse me with such matters. So chi is a function now defined on the integers. It's periodic with period q, and it's multiplicative, and the relation there holds similarly here because of that multiplicativity property. And you introduce an L function. This is Dirichlet L function, ls chi, summation chi n over n to the s. And it also has such a product. And let's look at a more fancy one. An object which is in GL2. So this is a function on the upper half plane. So consider this discriminant, or maybe Ramanujan function, which is defined as this infinite product, 1 minus q to the n to the 24 times q. If you expand out that infinite product here, mod q is less than 1, say. If you expand out that infinite product and collect terms, you get integer coefficients, which we call tau of m, and you get a series of this type. And if you write q as e to the 2 pi I, z in the upper half plane, then this function delta of z satisfies a transformation property which characterizes it essentially as a modular form. It's a holomorphic function. And if I take delta at az plus b over cz plus d, linear fractional transformation for a 2 by 2 matrix in SL2z, it transforms like this. This number here indicates to us that it's a modular form of weight 12, and it's a technical thing, it's a cusp form. It's got many other properties relative to Hecke operators, but which are encoded in the following identity. So if I write summation ls delta summation, this normalization, let me clarify something immediately, especially for the more algebraic members of the audience. My functional equation is always s into 1 minus s, so normalized so that I can understand sizes of numbers, so that special points, which we'll return to later, are s equals a half rather than what it might be s equals 1 in some notations. When I get to that, I'll clarify that. So that's the reason for the n to the 11 over 2 there. And this fact that this factorizes, of course, says something about the properties of tau mn in terms of tau of m and tau of n. And that was a conjecture of Ramanujan, who studied this function first. And that was proved by Mordell, that such an identity is true. All this for real part of s bigger than 1. Of course, I pointed out that the Riemann Zeta function, when appended with that Archimedean factor, gives us an entire analytic continuation. It's got a pole and a functional equation. What I'm pointing to here is that this function here has similar properties. And in fact, in complete generality, what is an automorphic form? Let me just describe it as follows. And it is, for my purposes here, important to introduce the general case. So what the first case was, let me just explain one point here. The first one had products here which in p to the minus s were of degree 1. This I could factorize into products of degree 2. And in general, an Euler product of degree m would come from an automorphic form on GLM. Now, you've probably heard a lot about the theory of automorphic forms on all sorts of classical groups. The main case, however, for the theory of L functions is GLM. This is because of certain philosophies and beliefs, which I'll return to in a second. So the general case, and the only case I want to consider here, is GLM, which captures everything for the purpose of L functions, is the following. The general L function will be a product over primes, and one can only work over Q to capture the general case, incidentally. That suffices to work over the rational numbers. It's a product of local factors like this, where these factors are products of degree m, where there are some numbers here, and those numbers are associated with f. They are computed by computing, they are eigenfunctions of Hecke algebras, and these numbers come out of eigenvalues of that action. So they are explicitly computable in terms of f. For our purposes, that's what I want you to note. And there's something that we want to append at the Archimedean place, and that thing we want to append at the Archimedean place is also a product of m factors, just like with the Riemann Zeta function, except instead of having an expression in p to the minus s, we have a gamma function, and it has got some parameters, which I've called here mu fj, and there are m of them. And so for each automorphic form on GLM, and what that means precisely is the GL2 example I gave you was a function on the upper half plane, or it's a function on SL2R divided by SO2. These are, with some transformation, these are functions on GLMR, which transform under a discrete group, which is defined through integers, in some periodic way. That's the notion of automorphic. These are mysterious objects, but the important point that I want to mention here is once we have an automorphic cusp form on GLM, for such objects, we know what we know for the Riemann Zeta function. That is, if we take these factors which are given through specific prescriptions and we multiply it by this part, the finite product, and the Archimedean place, then this satisfies a functional equation. There was something special about the Riemann Zeta function. This completed function goes into 1 minus s and another representation f tilde, called the contragradient. The most interesting cases are when f equals f tilde, incidentally. And factors in general emerge. I didn't give the functional equation for the Dirichlet L function, but these factors already emerge there, that we get an integer to the s minus a half and a root number epsilon f, a number of modulus 1, both of which can be computed. The integer q we call the conductor, and since I'm going to do something, describe some theorems here, I introduce probably something that's not so common. I'll call lambda f, the size, or the Archimedean size of f, is just the size of these parameters at infinity. I should have said that at infinity, when I have this function which is invariant under the SLNZ or congruent subgroup thereof, the function at infinity is an eigenfunction of differential operators. That's what, it's a function on a symmetric space, which is an eigenfunction of differential operators. That's the appropriate generalization of holomorphic. And the beautiful work of Hecker, who revived the theory of modular forms this year, Maas, who saw the more general case in the upper half plane, and in this case, Gaudemar and Jacquet, who proved the general case on GLM, shows that we understand for these L functions what we understand for the Riemann Zeta function. That is the analytic continuation and functional equation and what these factors are. Okay. Now, of course, in the theory of modular forms or automorphic forms, one major problem where there's been, as you know, tremendous progress is the problem of actually creating these. The philosophy, due to many people, but Langland certainly is the person responsible for putting, I think, the general setting. The philosophy is if you start off with something from arithmetic, like a variety defined over the rational numbers, and you define these local factors through counting points, let's say, some arithmetic data. Deniger described how you define a zeta function, Hesse V, zeta function as it's called. The philosophy is that that object you created there should be one of these L functions. And of course, a very fundamental problem, for which some progress, of course, has been made, a lot of progress, is to show that something's a modular form. That's one kind of problem. That's not the problem I'll address here. What I want to address here is we're given an automorphic form and an L function, and the problems I want to address are the following two basic problems. And I don't know that they're really analytic problems. They sort of, I would hope in the end, a mixture of analysis and algebra. I think that's what's appealing about these problems, is they appeal to people from all different fields. These are the two main problems, but I will say analytics since that's the direction that I come from. So the first one, I will call it the grand Riemann hypothesis. Certainly Riemann didn't conjecture this, so I should distinguish that. And that is that if we look at the zeros of the completed L function of any one of these are cusp form over Q. I should say, for those who might wonder about other L functions that may come, general philosophy is every L function in the world is a product of these, finite product of these. These are the basic primitive objects in the subject. So if you understand these for these problems, you're quite set. So the grand Riemann hypothesis would be that the zeros of the completed L function of any one of these all lie on the line and a half. Needless to say, it's not known for zeta and probably, therefore, not known for any single function. However, we're going to see that families, one of the themes, or the theme, that I've mentioned this and I'll keep on mentioning it, is even just to understand one L function, the progress seems to be to think of putting it in a family and then getting information about one by going to the family where we then get the information about all of them at once. So this is conjecture one, the grand Riemann hypothesis, which is a folklore theorem. It could, of course, be possible that the Riemann hypothesis is true for the Riemann Zeta function, but for not one of these. That would be a disaster. Not only would that be a disaster, for those who are not directly in the subject, I should emphasize that the Riemann hypothesis itself for the Riemann Zeta function is not very useful. It is a great problem. It must be that when you solve the Riemann hypothesis, you solve it for all L functions. All the millions and millions of applications, and there are hundreds and hundreds of theorems that are, if assume GRH, I'll call that GRH, then the following is true. They almost never appeal to the Riemann Zeta function alone. There are, of course, some, but they are the least interesting. So it would be a sad state if somebody found just one trick to just do the Riemann Zeta function, because that would have minimal implications. Okay. The second problem, certainly not stated by Ramanujan in this language, but in a specific case of tau of p is equivalent to it, is that those eigenvalues of the Hecker algebras, so in these local factors, yeah, I will use that one just now. So don't know why this particular side gets the favor that everybody wants to be on this side. But anyway, these alphas and the mu's, the absolute value of the alphas, this is some technical thing which you should ignore. The absolute value of alpha should be 1, and the real part of the mu should be 0. I think the first person to state this, at least in this language, and then after which the generalization is immediate, is Sarnak. And so these are the two main analytic questions, and I should say perhaps a little bit why they're important. I think I mentioned that, of course, there are many, many applications of the first, so and I think that's well known, but let me say just one word about the second. The second has many applications in number theory. I can even say it has applications in communication networks. There's something called Ramanujan graphs, which are constructed out of the knowledge in special cases, which I'll return to, of this conjecture. So it's even useful outside of number theory. That's very pleasing. And another thing which is a good reason to put these together, the special cases that we know of these, in the special cases that we know of these, we always get this result by reducing this conjecture to that conjecture, but not in this form, but that conjecture over the function field. I'll return to the function field, but it does indicate that somehow this is a much harder problem in the sense that this follows in special cases from that, an analog of that in the function field. Do I have any more comments about these two conjectures? So, of course, I should say that the second conjecture is known in the case that Ramanujan conjectured it, so the Ramanujan conjecture was solved by Deligne. In this case, this statement there is equivalent to the statement that tau of p is less than 2 p to the 11 over 2, and that was beautifully solved by Deligne. There were special cases known before. One should mention the name of Eichler, Sato, Ihara, who made reductions, and this particular case was eventually solved by Deligne. And another thing I would like to say, and it's a bit of my theme here, is that Riemann, this may not be so well known, but Riemann found this conjecture for the Riemann Zeta function by checking the zeros. So this is very much an experimental science as well. He checked the first 10 zeros. He didn't just make this conjecture in thin air. And certainly Ramanujan observed this from computing this function. And many of the most interesting conjectures around this, and I'll return to a few, are found, or maybe found philosophically sometimes, but then experimentation is what makes us believe them. And the role of the experimentation should not be underplayed or overplayed. It's there and it's important. Okay, so what do we know about this in this generality? As you might guess, we certainly don't know the conjecture. And in fact, there's one basic result we do know. All the techniques are based on that, or related to it. And it's the well-known theorem that, all right, we're trying to show all the zeros are on the line a half. The Euler products converge. This is not obvious in the general case, but it is known that the products converge absolutely up to the real part of S bigger than 1. So on the line 1, you might ask why that would be useful information. I'll say in a second why. But on the line 1, we know these functions do not vanish. So we have moved an infinitesimal amount toward our goal. And this goes back to Adamar, de la Vallée-Poisson, Dirichlet at a special point. Non-vanishing is already very powerful information, and Adamar and de la Vallée-Poisson proved this in order to prove the prime number theorem, along the lines indicated by Riemann, which is why I introduced the function. And I should say the proof here, I want to indicate one word about the proof of this, which works in general with some generalization of certain constructions, is it uses positivity, an argument where you construct, basically you show that if the function vanished at 1 plus it, you would have a problem at 1 plus 2 it by making an expression which has non-negative coefficients. Positivity or non-negativity, as you'll see, is the key feature. It entered already here. All right, now the bounds you get, I'll indicate in a minute why one might want bounds. The bounds you get, lower bounds say when it doesn't vanish, which are important when you use such a thing. Knowing something's not zero without having a bound is obviously some kind of useless information perhaps, so you do want to prove when it's not zero, you want to give a bound. The bounds are all the same. They're rather weak, but they're all the same. They're 1 over log of the natural parameter. But there's one case, and it's eluded everybody, and it's the case that I think one should be optimistic will be solved in not too long. It's this lacuna that the non-vanishing of an L function, a Dirichlet L function with quadratic character at the point 1, Dirichlet already proved that's not zero, but a lower bound for that is much weaker than any of the other lower bounds that we have. And there are good reasons for it. The method cannot overcome this difficulty, and that possible very close 0 to 1 goes by the name Ziegel 0, but I will call it here Landau Ziegel 0, because Landau in a paper that's before Ziegel already pointed to this method. And it's one of the most extreme violations of the Riemann hypothesis, and even that we can't eliminate as yet. However, if one looks a little more generally at L functions, I want to point out the following, that firstly Stark pointed out a long time ago in terms of special kind of zeta functions, Dedekind zeta functions, never mind what they are, that somehow this is the only bad case. This is the only kind of bad zero that can happen is for this quadratic character among some restricted class of L functions. And a very beautiful recent theorem, which has very powerful applications, is due to Hofstein, Lockhart, Goldfeld, and Lehmann. And it says that for a GL2 form, and L functions related to it, there are no Ziegel zeros. And that's highly not obvious. Roughly speaking, the LS chi's where chi is not quadratic do not have a problem at 1 because of chi and chi bar. And the feature is very similar here, but it's highly not obvious what f here might be self-dual, meaning, remember the functional equation related f to f tilde, the contragradient. It's when f equals f tilde, which is what's happening with a quadratic character, that the difficulty enters. Yet they show that there is no Ziegel zero, and it's a beautiful example of using GL3 to understand GL2. And, you know, this already is much more demanding mathematically to look at GL3. There's no complex structure and things like this in that situation. And you might, if you're really just interested in the upper half plane, and there's no question the upper half plane is delivered, just want to stay there. But you cannot. The symmetric square L function, as it's called, is really something that lives on the bigger group. So one really should take the more general view. It pays off. And so the Ziegel-Landau zero is really a phenomenon entirely associated with a quadratic L function, the one. So the best bounds in general are still those due to Dirichlet for LS chi, where chi. There's a slight improvement, but essentially that's the best bounds. I want to describe one piece of progress before I turn to the zeros and the first problem and make some discussion along it. Because I want to point out the kind of development that does happen, which is rather impressive. There is a conjecture called the Lindelof Hypothesis, which is a question of bounding the L function. So I have one of my LSFs here on the line and a half. The zeros are supposed to be in the line and a half. Here I ask what seems to be an analysis question. How big is the function on the line and a half? This might look like an obscure thing. Certainly it seems much less pretty than the Riemann hypothesis. And in fact, such conjectures which say for all epsilon there exists an C epsilon and doesn't tell you what C epsilon is, are not conjectures that can be falsified easily. So they don't fall in, this is not of the caliber of the Riemann hypothesis, but it's extremely useful, as I'll show you in a minute. And it's something we can make progress to and measure progress to in a more significant way. So this conjecture says that essentially the L functions, any L function in all its parameters, that is in the parameter t, which moves up the line a half, in the parameter lambda, which measured how big the Archimedean size of the automorphic form was, and in the parameter q, which is the conductor, this is all to the power epsilon. You must put that safety valve there, but other than that, the function's bounded. And that's called the Lindelof hypothesis, and the only reason I personally believe it is the Riemann hypothesis implies it. So we believe it's true, and I want to describe an application of an approximation to this. So in analysis, there's the three-line theorem which says if you have an analytic function, it's bounded here, then in the middle you can bound it non-trivially by a linear interpolation. That's called convexity bound. The convexity bound in here would give you that this is true in general with epsilon equal to a quarter. That's trivialities. Getting underneath the quarter is what I will call subconvexity. Now, this is not just gymnastics. There are problems where, and I think the subject does suffer a bit from the image of people improving exponents. And I want to say a word about that, if you don't mind. Firstly, of course, if you're improving exponents by new methods, and all you're doing is improving exponents, it's still very interesting if the technique is novel. However, there are a number of problems, and I will describe two of them, which are just at the border where any improvement gives you a complete theorem. And those are, of course, the exciting problems, and those problems, and this is an example of going around the mountain. If I knew the Riemann hypothesis in the problem I'll describe here, the solution of the problem is immediate. If I knew the Riemann hypothesis, there's no Ziegel zero. But there are these problems where just improving, and of course you're stuck there because you need a fundamental breakthrough, a fundamental idea, does lead to the solution, and those are the important improvements. And while in GL1 getting under 1/4 is, as I was saying in the beginning, is got a long history. Recently, in a very beautiful series of papers, Duke, Friedlander, and Ivanic have now completed a similar theorem in GL2 in all the aspects. And in particular, you can prove that with a quarter minus delta. I don't even declare the delta. It's not important. As long it's explicit, it's 1/20, say, but it's under a quarter. And to show you how useful such a thing might be, is it's got applications to quantum ergodicity, which I won't describe, complete solution of a problem, and to a problem which I think Wiles might have mentioned, but just let me repeat it here because it's a good example of all these features. The problem of which numbers are sum of three squares was resolved by Gauss. But if you change to a general positive definite quadratic form with integer coefficients, this was completely open until very recently. Well, not so recently. This was solved maybe 10 years ago. But by this method only recently. By Ivanic and Duke first, but in this connection, they all related these things. So we want to know which numbers are represented by Q. And Gauss really picked on one of the miraculous forms in the world, that you can really answer that exactly which ones are represented, which large numbers, small numbers you should check by hand. Well, this improvement there, just over a quarter, allows you to resolve this problem completely. We now know there's one little caveat, and that is it's not effective. And it's not effective because of that damn Ziegel zero. That is to say, we know which large numbers are represented by this form, but we cannot say what large means. It's not, in principle, from the method of a proof, possible to say what large means. So you might wonder what has been proved. I'll let you ponder that. But every sufficiently large number one can determine in purely simple terms, check whether this is solvable modulo L for every L, which is an easy exercise. All right, to get to the topic of the zeros and some insights about them, I want to discuss the distribution of the zeros. This has a long history. It starts with Riemann himself. So let's turn to zeta for a minute. Let's write the zeros as a half plus I gamma, hoping gammas are real. If I talk about a numerical experiment, you can well assume that the gammas are real, because if there was one found off the line, I would have started my lecture that way. So if I'm going to describe an experiment, certainly you can assume gamma is real. And you order the gammas. Gamma 1 is bigger than 0, less than or equal to gamma 2. And because of the functional equation back into itself, gamma of minus j is minus gamma of j. I just point out that gamma 1, which was found by Riemann, is 14. This is very large for the lowest zero of a zeta function. The Riemann zeta function has the highest lowest zero. And this actually was the cause of a complete misconception of 19th century mathematics. People were trying to understand the prime number theorem. There's a function called pi, which is the number of primes less than x, and li, which is the logarithmic integral approximation. And these two functions, pi was always less than li, and we know that it probably changes at 10 to the 320 today, so you'll never see it change. These poor fellows last century were computing it at 3,000 and making conjectures that pi is always less than li. It's in fact false, and the reason it's false, now that we understand it today, is because the zero is so large. If that zero were much lower, you wouldn't have had that effect. So Riemann, this is a very large value for the lowest zero. But that's not what I want to describe here. I want to describe the high zeros first. So let's count the number of zeros whose height is less than t. And what Riemann already showed, knew anyway, is that it's asymptotic to t log t over 2 pi. So that means when I'm high up at height t, they're roughly log t over 2 pi zeros, which means that their spacings must start to get small. I want to study the statistics of the spacings, and you'll see in a minute why. So I do what is commonly called now in mathematical physics, I unfold them, I renormalize that so the mean spacing is 1. So instead of looking at gamma j, let's look at gamma j log gamma j over 2 pi. Now if you think about it, the mean spacing between these numbers will be 1. And I want to study the local spacings between the zeros. What's the distribution? How often is this difference between 1 and 3 as I move up and look at many, many zeros? So for example, let's look at the consecutive spacing, gamma j plus 1 hat minus gamma j. That's a real number, and then I draw a histogram of how often this lies between two numbers. And the reason I'm doing this is there's a remarkable development, this is also 10 years old, by Odlyzko, who experimented with this. He's been doing this for quite a while, for 10 years, and he has found that this follows a specific law. A law in statistics means a distribution. And this was done with a Cray. This is the 70 million zeros beyond the 10 to 20th zero. And what he finds with the dots here, I hope you can all see the dots, that's the histogram of what he found from the data with the zeros of the Riemann Zeta function. And it fits some solid curve. And the solid curve is trying to tell us something. The solid curve isn't something that, well, maybe some of you are familiar with, but it's certainly something that not most of us were familiar with. It's called I'll call it the circular unitary ensemble consecutive spacing distribution. I'll show you what it is in a second. It's something from mathematical physics. The fit is perfect. You take any other variant, you look at the second nearest spacing, you look at any other statistic, I'll leave that up on the side. It seems that the local spacings know about some statistical theory in random matrix theory. So let me just say a word about what that is. The circular unitary ensemble, this is the spacing distribution between the eigenvalues of a large n going to infinity rescale, just like we unfolded there. So it's a spacing distribution between the eigenvalues of a very large unitary matrix, typical, where I choose that matrix at random. So I choose n extremely large, I choose a typical random matrix with respect to Haar measure, and I compute that spacing distribution. That is not an easy thing to do. This was solved by, in physics, this is called the Wigner distribution, that solid curve. It's a funny subject. Wigner guessed the answer, it was wrong. Gaudin found the right answer and proved it, but it goes by Wigner's distribution. It was even the wrong conjecture, but I will call it the Gaudin distribution if you don't mind. So Gaudin, Mater, Dyson worked on this heavily. And it's given by a determinant of operator on infinite dimensional Hilbert space. It's not something that's an elementary function, though it was discovered by Jimbo and his co-workers that it is expressible in terms of Painlevé 5. So it's perhaps could be considered a special function. In any event, the Riemann zeros know about it. And I want to discuss why. The analytic determination of the correlations, this experiment done by Odlyzko was not done in a vacuum, so to speak. He didn't just start doing this. He was, of course, oh, incidentally, all the zeros he found were on the line and a half. I mean, that's the first thing he looked. This experiment he did was based on a calculation done by Montgomery for the pair correlation. He looked at the distribution of all differences of the zeros. in 1974, and he was able to compute this in some restricted ranges, note, so he wasn't able to understand it completely, but in restricted ranges. And what he found, it was pointed out to him, is the same as what is for a random matrix, which is why Odlyzko decided to compare the data with that. And recently, Rudnick and myself were able to compute all the n-level correlations, again in restricted ranges, and we did this for any L function in the world, not just the Riemann Zeta function. And quite remarkably, we kept on finding that we tried to really compute all the correlations in order to maybe see if there's a difference. We were expecting a difference, but there's some universal law we found. We always got the same answer. It's universally CUE or GUE. Let me show you Rubinstein's data. Because that's still in restricted ranges, maybe it's important to experiment and make sure that this feature is really there. And Rubinstein, a student finishing his degree at Princeton right now, has computed this distribution. It's the same GUE or CUE distribution, and this is for the Ramanujan L function. So he's taking beasts of different L functions. This is an L function of an elliptic curve, which is also an Euler product of degree 2. And the fit is always the same. Rumely computed Dirichlet L functions. So whichever way we look at it, there's only one answer that comes out. So I'll call this the Montgomery-Odlyzko law. The law that the high zeros of any L function whatsoever follow only one behavior. Of course, one gets excited by that because they're not behaving like random numbers, they're behaving apparently like eigenvalues of a matrix, which means, of course, as you heard in Denninger, one wants a spectral interpretation of the zeros, and this is some little bit of evidence for that. Okay, so I want to describe another setting, and I will return to the Riemann Zeta function and those in a minute. But in another setting, one knows much more, and one can ask about this kind of feature, and it sheds tremendous light on where it comes from and what's the cause of this phenomenon and what's going on. So this is the function field analog of the Riemann hypothesis that I mentioned earlier, which was used in the special cases to prove the conjecture 2. I'll just describe the simplest case. Denninger mentioned some of the, certainly a lot of these in his talk. So in Artin's 1923 thesis, he had the idea of replacing the rational numbers by the field of rational functions in T with coefficients in a finite field FQ, and you take a finite extension of that, just like you do in the case of the rational numbers and an extension, and you form a zeta function, and it's more convenient to use the parameter T rather than S here. And it's defined in a way, you subproduct over all places or primes of 1 minus T to the degree to the minus 1. And Artin introduced these and checked for just many elliptic curves, hundreds of them. Again, this example was first done numerically. I emphasize that. These things are found experimentally first. In any event, soon after that, Schmidt, developing some algebraic geometry of curves over finite fields, was able to show the zeta function is a polynomial of degree twice the genus of this curve, or these are the rational functions of a curve over FQ. You can view it in either way. It's got a genus, and this zeta function is a polynomial. It's got poles just like the Riemann zeta function. This is the completed thing, and it satisfies a functional equation. And the key thing is the genus, because it tells us that this polynomial is degree 2g. And Artin had already conjectured that the analog of the Riemann hypothesis is that all the zeros of this polynomial, which has integral coefficients, all lie on the circle radius 1 over root q. That's a symmetry axis, just like for the Riemann zeta function. And as most of you, I'm sure, know, this was proved by Weil during the war. Great achievement. And we understand where it's coming from here because we have a spectral interpretation of the zeros through Frobenius acting on cohomology groups associated with a curve. So there's a lot of machinery here. And Katz and I have written a book. So this is joint work with Nicholas Katz. And most of the rest of this will be such. He's a colleague of mine, Nicholas Katz. Is about understanding first what that remarkable feature is, this universal law, in this function field case where we understand things much better in the hope of it to explain to us what really is going on. So what we found is indeed that law, we prove, does arise in this case, and we find the cause of it in the function field. Our theorem is that unfortunately, we have to let Q also get large. But let me not spend time on that here, so it would be much nicer to not have that, but I should point out the following, that you can, of course, we have only finitely many zeros for a fixed zeta function of a curve over a finite field. So I can't expect the spacings to follow some universal law. So you might say to me, just let the genus go to infinity, that'll introduce more and more zeros. But it's easy to show that if you just take curves at random of genus G, you could, not at random, but carefully at genus G, you can create anything you want. So our theorem is the only, or one possible general truth, is that the typical curve of large genus and large characteristic, Q just has to be big in size, has the property that if you take it, typical, you just count all curves. So this is done by looking at moduli space of curves of a fixed genus. You take such a curve and you take it at random with counting measure and you look at the spacings, it will look like this when G and Q get large. So this universal Montgomery-Odlyzko law is in fact true in this sense in the function field. More importantly, we understand where it's coming from. This universality comes from a universality in scaling limits of the monodromy. So let me just say the tools which are used in the proof. We use, firstly, the fact that if I take a family of curves here, all curves over FQT, over FQ, I take curves of genus G, this forms a natural family. And in the family, I look at pi1 of the family and its representation on H1 of the curve. This is where the spectral interpretation takes place. You get a monodromy representation, and you get a group. And this group is crucial in explaining this. That group happens to be, in this case, the full symplectic group for fixed genus G. And that's crucial that this is a big group. That you'll see in a second why. Because there's a beautiful theorem, Weil2 is the name of the paper of Berlin, where he proves these general Weil conjectures. If you apply that theorem carefully, you will find that using that you can get equidistribution of the Frobenius, and the determinant, the characteristic polynomial of this Frobenius is the zeta function. So you get these conjugacy classes to be equidistributed in the monodromy group. And then you are left with some scaling limit, physics type problem, when the genus goes to infinity, and that Katz and I are able to resolve for the symplectic group, and in fact for any classical group. And that's an important point, is we show that no matter what the classical group is, unitary, orthogonal, symplectic, special unitary, as long as it's getting large, the spacings between the typical member of this group, as their size goes to infinity, follow that law. So while this law in the physics literature is associated with Hermitian matrices, this or that, the real cause is there's a universal feature in classical groups. It was crucial here because everything's symplectic in this particular picture, yet we're getting this what's called Gaussian unitary ensemble. So we were confused about that, but now that's completely explained. It's the reason all the L functions there have the same behavior, at least in the function field, is this universality here. But this also allowed us to look at something which might tell us what the real symmetry is, something more subtle. So to do that, we, in the function field, looked at the following. And then I will return to the number field. This lecture is mainly about Q. So instead of looking at all the zeros of the zeta function of a curve of large genus, let me look at the lowest zero, the zero near the central point, a point that, which we'll discuss a little bit later. So let zeta tk be such a curve, and let k, these fields, they can be associated with curves. Let this curve lie in some family, and let me look at the distribution of the zero nearest to 1 over root q, which is the middle point of a functional equation. And again with a scale, which is to multiply the closest zero on the circle by q over 2 pi, so that it's roughly the right size. And let me then look at the behavior over the family and try to see what happens when the genus goes to infinity, which is naturally formulated in, say, taking FQT and looking at all quadratic extensions of that. That would give me all hyperelliptic curves of higher and higher genus, for example. That's a good example of this feature. And we compute these scaling limits using, by the way, the methods of the physicists are crucial here. And we find the answer, and we find that for each family in the function field, if we can compute the scaling limit of the monodromy, we find what the distribution of the zeros near the central point is over the family. And it's completely dictated by the symmetry group of the family. And much to our delight, this answer is not universal. It depends on the symmetry. So if I go back now to the number field, I can now look for the symmetry we're looking for by examining the zeros. This is much more sensitive than going vertically. So I call this the problem of low-lying zeros in a family. And, I should have said that main theorem, subconvexity, uses families. I'm supposed to say every time that we're using families, and I forgot. The theorem of Duke, Friedlander, and Ivanich is heavily based on a method of families. Here, I'm really taking the family seriously and trying to find the symmetry group associated with the family. In the function field, this comes from this monodromy, and it's understood. So let me look at a number field. Now, you're going to jump up and say, what do I mean by a family of L functions in the number field? What I mean right now, because we only have 8 families that we've thought about very carefully, I'll give you 3 of them. Everything I say works for these families beautifully, is what I describe in specific examples. I don't, of course, have the setting where I can tell you I have a base and a family of, the algebraic geometry hasn't entered. However, you'll see that very concrete things enter, which we will prove. Nevertheless, so suppose I have a family of L functions. They may be Dirichlet L functions, say with chi squared equals 1. And let me write their zeros as a half plus I gamma fj. And the gammas, let's just for a moment, for the purpose of description, assume they're real. And let me look at the lowest zero. And again, I must scale. It might not be obvious why this is the scale, but when in any analysis and proof this enters. The right scale always is to take the zero, the lowest zero, say, this was supposed to be gamma 1f, times log of the conductor of the form divided by 2 pi. So we must compute the conductor of the form. That's the correct rescaling. And I get numbers which are, as I vary over the family, a set of real numbers. And I can ask what their distribution is as I go in the family, and the number of elements in the family increases by some ordering. I should say that in the function field, these questions are all answered. So we can predict what should happen. We know what happens there. So let me describe 3 families where this has been very successful. The first family is the just family of Dirichlet L functions with quadratic character. So this looks like a very abelian thing. I just take LS chi squared is 1. The conductor is Q. There's one primitive character of this type, and I let Q ordered by size, and X go to infinity, and I look at the lowest zero. According to our function field analysis, this should follow a scaling limit of symplectic groups. The symplectic form immediately enters on the curve through the cycles, intersections of cycles. So the symmetry group in the function field is the scaling limit of symplectic groups. I'll denote it by SP infinity. Just because I've been talking, I'm just giving some specific examples, just because I'm talking about this example of twisting the Ramanujan. Let's look at S delta twisted by chi, tau v over n to the half chi of n to the minus s. That's what twisting by chi means. Chi squared is 1. Here the conductor is Q squared. And again, we can compute in the function field what happens in this example. And there the symmetry group, which is a symmetry of the family, makes sense. And it's a O infinity. It's a scaling limit of orthogonal groups. And the distribution of the low-lying zeros is going to be entirely different as we computed. They are entirely different, so we should expect to see different behavior. So Rubinstein, in the same thesis, of course he has a beautiful way, developed beautiful ways to compute zeros of these kinds of things, computed this and looked at the lowest zero and compared it. This is LS chi squared. So he looked conductor up to about 10 to the 12. This is not the GUE distribution. This has got the same profile, but it's something quite different. It's something that comes from our theory. You have to compute some Fredholm determinant on an infinite dimensional space, and you finally get this curve. And lo and behold, this fits perfectly. On the other hand, if I twist the Ramanujan by chi, this is a different family. The function field there suggested it was orthogonal. I'm twisting here where the sign of the functional equation is 1. With the orthogonal group, it's best to break into the even functional equation and odd functional equation separately, and I just show you the even. Notice it's completely different. The zeros tend to like to be near 0. The gammas rescaled like to look near 0, and they follow a curve here, which is coming from the same theory, and in the function field it's there. Ah, yeah. Here is 1. And here is 1. Thank you. Yeah, they're different scale. Yeah. hang on. Yeah, I'm used to interacting with the audience. It's kind of tough here, but I see that will happen anyway. Okay. Oh, the other. That's one, and that's one. Yeah, they're different scales. Maybe that was poor science. Yeah. Ah, sorry. Which one? The last one? Okay, so I'm expecting, this is my, I'll call family F1, that's quadratic characters. Family F2 is a twist of a GL2, for those experts, non-CM type, by quadratic characters. And the by the way, just like these other conjectures, we first went to numerics. These are things we didn't really expect to happen, but they happened beautifully. And of course, if I look at different statistics, the predictions are all perfect here. So for these two families, the theory is perfect. And now let me look at a family which we can prove much more about, and for which we have no numerics. It's quite hard to do numerics on this. Let me describe what this family is, a third family, and for which we don't understand the function field, but the symmetry is coming through what we can prove. It's the following family. Instead of taking the modular group, let's take these congruent subgroups which play such an important role. These are the subgroups of the SL2Z where the bottom left corner is divisible by n. I'll assume, say, n's prime for simplicity. And then I can form this quotient x naught n. This is a Riemann surface of genus roughly n, over 12 or something. And I'm going to look at n very large. This curve can be defined over the rational numbers, so I can think of it as an arithmetic, as a curve over Q. Okay, the family I want to consider are all the modular forms of weight 2, or holomorphic differentials f of z dz, which are Hecker eigenforms, and their LSFs. So that is a family which I claim we can show, again in restricted ranges, has an orthogonal symmetry. So it's behaving like the second example there as far as its low-lying zeros. Okay, so those are three families. Now, instead of describing, what I'm pointing out here is Ivanic, Lua, and I, in a paper that's being completed now, are able to prove that these distributions in these families behave according to these symmetry predictions in restricted ranges. We don't entirely resolve the distribution question, just like in the case of the highest zeros of the Riemann Zeta function, we are not able in n-level correlations to deal with the whole range, only in restricted ranges. But these ranges are really big here, and big enough to actually capture the difference and see that you really have different symmetry classes, especially in the third case where we don't have any numerical results. So rather than describe those technical results, let me describe consequences of them. These are unconditional theorems. And I'll just, because I want to emphasize that besides the philosophy of what the zeros are looking like, and this is giving us such, this immediately points to directions where you can prove things and use tools along these lines. So I will just say the following. What I'm trying to point out is, given a family of L functions, and just, if you don't like automorphic forms, though you should like it, I think to answer Waffer said the unreasonable effectiveness of mathematics in physics, and he attributed to Einstein, it's actually Wigner, but I should say the unreasonable effectiveness of modular forms in number theory is what the status of today's, or the last few years. So the family here, if you've never seen modular forms, just think of the first family, but the general families are actually even more interesting. Given a family, we have a symmetry group, which I'm suggesting, which would then predict the distribution of the low-lying zeros. So I'll just call the symmetry conjecture for the family in this case. And of course, the evidence I'm telling you for this is numerical. In the function field, it's proved, and we can prove in restricted ranges that this behaves the way that this is predicted. Okay, let's turn to an application of this, because it connects a few things. The distribution of the low-lying zeros in a family is, of course, the zeros near the point 1/2, the center of the critical strip. In particular, it tells me how often I'm equal to 0 at a half. And the point at a half is a very special point and beautiful point in the theory of L functions. There's a beautiful conjecture, also found numerically, I should add, 1959 or so, when computers were first brought to us, and Birch and Dyer and Birch experimented and discovered the following lovely conjecture. It's called the Birch and Dyer conjecture. It relates the order vanishing of an L function of a certain type, like the family 3 that I had there, to the ranks, I'll describe it in this case, of elliptic curves and abelian varieties. And one of the major developments in the subject are partial solutions of this. Partial solutions which are so strong, again, leading to complete solutions of problems. And it starts with Coates-Wiles, Gross-Zagier, Colley-Vaughan. These are results which are very powerful, giving partial proofs of these conjectures. I will use them freely, just so that I can give an application of non-vanishing or something like that, which is the next section, of those results to this kind of question. So I look at x naught n, that's a curve, it's defined over Q. I look at its Jacobian, that's an abelian variety. And it's defined over Q, and it's an old theorem of Weil also in his thesis, I think, that this is a finitely generated group, so it's got a rank. And that rank is a mysterious and very interesting thing. And there are two parts that I want to discuss. The first is, what is the biggest quotient, defined over Q, abelian variety, quotient of this abelian variety, which has only finitely many points? This is a quotient that was studied, well, part of this quotient was studied by Maser with lovely success, and more recently, Morel, who gave a lecture yesterday, or the day before, used it, this exact quotient. The question is, how big is this quotient? If we have the symmetry conjecture, you'll see exactly how big it is, but because we have approximations to that, we obtain rather strong results. So this is a theorem of Ivanic and myself. It's being written up, I'm afraid. Can't give you a paper right now, but the announcement has been out. That this m naught n, this biggest quotient of rank 0, is at least 1/4 the dimension of the Jacobian, say n's prime. It's very big. It's quite big. Now, if you have that symmetry conjecture, and in fact, Brummer, who numerically experimented with this, you quickly led to that should be dimension over 2. And what we can prove, it's at least 1/4 the dimension. Our interest in this, in part, was, and we knew this from the start, that if we could improve the constant here, now I said in the beginning there are these, you get to a barrier and then you want to go over. Here is one of the most, let's say, pregnant cases of this. One's right at the border here. If you could improve that quarter to any bigger numbers, then you would show there are no Landau-Siegel zeros. It's remarkable that it's all related in any way. In any event, at this point, the approximation to the low-lying distributions imply that the dimension's at least the dimension of J over naught n. Similarly, if you had those symmetry conjectures, you would get that the rank of J naught n is roughly the dimension over 2. The reason it's a half is half them have even functional equation and half have odd. That's really the crude feature here. And one can prove unconditionally, Kowalski, Michel, van der Kamp, using some of the techniques here, show that the rank is at least 7/16 the dimension. That's quite close to a half. This doesn't have the implication. This, however, is a rather striking result. One is quite close. So these approximations lead to understanding these arithmetic of J naught n, at least its size. So one more example of non-vanishing. I haven't spoken about conjecture 2. Quite remarkably, families, as I was saying, just about any aspect of progress. The proof of Ivanic and I are heavily involved in averaging over the family and positivity. These are the two themes, positivity and averaging over the family. Here's another example, also proved by family. The best results known to conjecture 2. So it's an approximation in general to conjecture 2, which was the Ramanujan conjecture, follows from looking at a slightly generalized family. Instead of looking at F, one forms something a little more complicated. F tensor, F tilde Rankin-Selberg, it's some technical thing, twisted by chi. So you fix your F, you want to prove that the alphas are all 1 and the real parts are all 0. This we don't know how to prove, but if we can get an estimate for it, how close the real part is to 0, that already in many cases suffices to resolve the problem you're trying to resolve using this. So the family that is introduced here is chi, one-dimensional characters mod Q. So Lua Rudnick and myself a few years ago showed how to use this family with some positivity and non-vanishing to obtain a very general method which leads to the best known results on Ramanujan. For example, let me give you one example of this where it's very concrete. Suppose you look at that x naught n, this is x naught n, and think of it as a hyperbolic manifold, the upper half plane divided by gamma naught n. This is a hyperbolic surface with many cusps. And you look at the Laplacian, this has got a curvature, constant curvature -1, I'll be 2 minutes. You look at the Laplacian on this, and you look at the lowest eigenvalue. The Ramanujan conjecture that I stated in this specific instance is a conjecture of Selberg that lambda 1 is greater than or equal to a quarter. An extremely important conjecture, this even in the special case. So what this general analysis does is it proves that lambda 1 is greater than or equal to 21 over 100. Well, it's getting quite close, but much more importantly, the bound that was known for many, many years, and the only bound was 3/16, and it was very important to get beyond that, that's due to Selberg, in order to apply to resolve problems about Kloosterman sums completely. So this was a case again where you're at the border, and so it's not so much that number, it's that that number is bigger than 3/16 that's important. And as I say, this is again based on families. You look at this family, and I'm running out of time, so I was going to give one proof, or idea of a proof, I won't. So let me just conclude here. I want to discuss this symmetries in families. So let me return to the family 1, F1. That's just the simplest of all, the set of LS chi where chi squared is 1, for which the symmetry, we have overwhelming evidence, I would say, that there's a symmetry, or at least the low-lying zeros follow as if there was a group gluing these L functions. Of course, it's possible that this is just a very clever way of predicting the answer. We can prove it's right to some extent. I'd like to believe that that's not the case, that in fact it's pointing to the fact that there is some kind of glue that we're looking for, which glues these, and that would be very promising for two reasons. Firstly, let me say something about symmetry, is the zeta function lies in this family. If you want to understand the zeros and the symmetry associated with one member of the family, you should try to put it in as small a family as possible. So if you look at zeta, it lies in this family, and hence, because the corresponding symmetry is symplectic, it must predict that if you gave a spectral interpretation of the zero, families, why this is an up note, why I'm optimistic about this. A, it's the only thing that's successful recently, and B, one should not forget that in the function field, the proof of the Riemann hypothesis does go through this, in general, does go through this. One does not prove it for one L function or zeta function at once. One puts it in the family, then uses this monodromy as a glue so as to conclude it for all of them at once in Deligne's proof, which shortcuts a program, let's say. So this family idea, if there is such thing between these L functions, is, I think, a very promising hope. Thank you.
Well, as time is moving on, I think we won't have any questions. Talk to Peter after if you have them. It just remains for me to thank Peter for his fascinating lecture. Thank you. Very nice. This result about single zeros and the dimension of...
No,
in other words, if you have a lot of...